Counting particles remediation. There's 5 questions here that are similar to the questions that many students struggled with during the test. The numbers have been changed and the questions are slightly different, but they address the same skills and knowledge as the questions from the test. Number 1, a form of phosphorus called red phosphorus is used in match heads. When 0.22 grams of red phosphorus burns in air, it forms 0.51 grams of phosphorus oxide. Use this experimental or empirical data to answer the following questions. So we have phosphorus oxide. It's made of phosphorus, and there's 20.22 grams of that, and it's made of oxygen. And the first question says we need to figure out how much oxygen there is. So we're going to obviously subtract those two numbers. So we're going to say 0.51, and we're going to subtract 0.22 grams, and our final answer, doing the math, is going to be 0.29 grams. That's how much oxygen we've got. So they told us we had 0.22 grams of phosphorus, and we're going to set up a table. We've got 1 mole, and if we look on the periodic table here, and it's 30.97. 30.97 grams. We can see here the grams are going to cancel. So 0.22 over 30.97. So it's 0.0071 moles. We just worked out we've got 0.29 grams of oxygen. We're going to change that into moles. We need to go to the periodic table and find oxygen, 16.00. Grams cancel, 0.018 moles. Now these numbers, from these numbers it's not obvious. The mole ratio is not obvious. So we're going to take the bigger one and divide it by the smaller one. So 0.018 divided by 0.0071, 2.53, we're going to call that 2.5. So the amount of oxygen is 2.5 times the amount of phosphorus. But we can't really write a formula like this. We can't say PO 2.5. And we can't round 2.5 up to 3. That's too much. So we can preserve the ratio by just doubling everything up. So the PO 2.5 becomes P2O5. And there's our empirical formula. Number 2, hydrazine can be used as a rocket fuel. A sample of hydrazine is found to contain 5.6 grams of nitrogen and 0.8 grams of hydrogen. The molar mass of hydrazine is 32.0 grams per mole. Determine the empirical formula and the molecular formula. The question in the test was dealing with a different compound, but it's the same principle. So let's start with our nitrogen. We've got 5.6 grams of nitrogen, and we want to change that into moles. If we look at the periodic table, nitrogen 14.01 grams cancel, 0.40 moles. So we've got our nitrogen. Now we're going to do the hydrogen. We've got 0.80 grams of hydrogen. We're going to take 1 mole. Hydrogen, by now you should know it's 1.008. I'm just going to round it to 1.01 grams. Grams cancel. So 0.79 compared with 0.4. If we think of that 0.79 as 0.8, the mole ratio is obvious. It's a 2 to 1. 0.8 is 2 times as much as 0.4. So when we write the formula, the N is going to get just a 1, or we'll leave it off, and the H is going to get a 2. So NH2, if you say H2N, that's also fine, but this compound is actually written with nitrogen first and hydrogen second, and that very often happens when hydrogen is involved. The element on the right is written first, which in this case is nitrogen, and then hydrogen. But now we need to look at the molecular formula. They gave us the molecular mass, and they said the molecular mass or molar mass is 32.0 grams, and we need to get the mass of NH2. So we already know nitrogen is 14, hydrogen is basically 1. I'm going to do a bit of rounding here. It's going to be 1, but there's 2 of them. So we can see the total mass of NH2 is going to be 16. So 32 over 16 grams is going to give us 2. That means our molecular formula is twice as big as our empirical formula. So our empirical formula is NH2. Our molecular formula is going to be N2H4. Number 3, when butane burns in oxygen and produces carbon dioxide, water, and energy, balance the equation. In the test, you had a different compound. It wasn't butane, but the same principle is involved. So in a combustion reaction, you want to do the oxygens last. So let's start with the carbon. I'm going to start by putting a 4 in front of CO2, which is going to give me my 4 carbons, which will balance the 4 carbons on the left-hand side. Then I'm going to put a 5 in front of H2O, because 5 times 2 is going to give me 10, which is going to balance my hydrogens. And now I'll look at my oxygens. And I'm going to go to the right-hand side first, and I'm going to look at my total number of oxygens. On the right-hand side, I've got 4 times 2, which is 8, and I've got 5 there. So if we add the 8 plus the 5, I get 13. So temporarily, what we're going to do is we're going to put a 6.5 in front. 6.5 multiplied by 2 is going to give me 13, and so everything's going to be balanced. What we do now, though, is we say if we multiply everything by 2, it's going to preserve the ratio of the coefficients, but it's going to make everything whole numbers, and so that way everything is going to be balanced. Question 4 deals with observations that prove or could prove that a chemical change has happened. These images represent those 4 changes. They don't all have to happen in a chemical reaction, but they could. And they don't necessarily prove that a chemical reaction is happening. They could prove it. The first one, a release of energy. Now, we could also get an absorption of energy in a chemical reaction, but that picture speaks release of energy. The second one is the formation of a precipitate. You can see how the precipitate is sinking and falling to the bottom of that test tube, and that's what precipitates do. So, forming a precipitate. Then we've got an obvious release of gas, which we can see by the bubbles. And the last one, we've got a clear liquid being poured into a solution and it's changing color. So there we have a color change. These are the 4 things that you can possibly observe, which means you can see them, hear them, feel them, that prove that a chemical change is happening. Only these 4 observations can prove that a chemical change is happening. Sometimes more than one of them is happening at the same time. Like the release of bubbles here, that test tube is probably getting a little bit warmer, but we don't have any evidence of that. Precipitates, when they form, you very often get a color change as well. So multiple of these can be happening at the same time, or just one of them can be happening. But you only want to choose from these 4 observations if you are asked to demonstrate that a chemical change is happening.